He got a PhD from IFT UNESP, and we were colleagues during those years. After the PhD, he was a postdoc at CERN and IFT UNESP. Nowadays, he is a researcher at UNESP and a member of the CMS collaboration, also the Compact Muon Solenoid collaboration, and the project SPRAS, São Paulo Research and Analysis Center. He received several research grants, and in 2019, he received the CMS Achievement Award. Today, he will talk about dark matter and colliders. Thanks a lot, Thiago, for accepting our invitation. And as I mentioned, I hope to see you also in person in Natal soon. And please go on when you are ready.
Thank you very much, Thiago. So since I hadn't shared, now I have to do some work to manage to share again. Just 30 seconds. Here we go. Share and share preview. Yes, should be working. Can you see it?
You managed.
Yeah. It's okay.
Okay. So thanks for the nice introduction. I will be talking about BSM physics, and particularly dark matter search in colliders. So this is supposed to be a very wide net seminar, so I feel obliged to first give a very, very short introduction to dark matter, okay? So what is this dark matter that we are supposedly searching for? I like to say that dark matter is a stand-in name for a number of unexplained gravitational, astronomic, and cosmology unexplained phenomena. Now, I am a particle physicist, so I'm going to take the viewpoint that these phenomena are explained by some kind of new particle, which should have some properties. But this is my viewpoint, and then, because again, I do particle physics, so I'm interested in searching for a particle that fits the bill. But remember, all that we have is a set of unexplained phenomena related to gravity working in ways that we are not used to, and that are, in a sense, unexplained. So what are we talking about? If you look at the slides, I'm looking to the right here because my slides are here, okay? If you look at the slides, you will see that there are many different phenomena pointing to this so-called dark matter. So you have rotation galaxy curves, you have lensing, which should be explained by some kind of matter that makes light bend in a way different than what we expect. We have the so-called bullet cluster, which is a cluster of galaxies where the dark matter and the galaxies that make the cluster seem to have separated during the collision. And we have the large-scale structure of the universe, which it seems, according to our understanding of gravity, of general relativity, of the lambda CDM model, that of cosmology, that it's impossible to have the structures that we have in the cosmos if we don't have something which is dark matter. Now, pay attention to the fact that all of these phenomena are at very, very different scales. So it's a bit of a leap of faith to say all of these are actually explained by the very same phenomena. But we are going to choose this approach in order to be economical. It can be shown that the so-called lambda CDM, or CDM stands for cold dark matter of cosmology, more or less addresses all of these phenomena correctly. Assuming that dark matter exists in the form of a new particle and it explains all of these different gravitational phenomena, what kind of particle should fit the bill? And this is essentially, I'm just rehashing here for you everything that is in the particle dark matter book from Profumo, okay? So if you want a much better explanation that I'm capable of giving you, just go directly to the source. The gross features of a dark matter candidate, first, it has to be dark. What does that mean? means at least that it has to be electrically neutral. Why? Because we don't see this missing matter in the sky. We don't see the gravity. We don't see whatever is making gravity behave in a way that is different from what we expected. So it doesn't interact with light, so it's dark. If it doesn't interact with light, of course, it has to be electrically neutral, but also this means that there should be some limits on its charge. It actually could be, for instance, milli-charged, and limits on its electrical and magnetic dipole moment. Also, it has to be collisionless. Why is that? Because one of the characteristics is that this thing doesn't interact with itself very much. It doesn't clump. It doesn't make gigantic planets, gigantic stars of dark matter. So this translates into limits into the self-interaction of the dark matter as a ratio of its mass. It has to be confined in kiloparsec scales. And it has to be such that if you add it to the mix of the universe and you calculate the stability of bound systems, it has to allow for these bound systems to be stable, and it has to be confined in these kiloparsec scales, which translates into this classical and fluid, requirements, which in turn translates into limits in mass. But you can see here that these limits in mass, they are actually very, very wide, from a couple EV or even a ridiculous fraction of an EV, depending on the spin of the positive dark matter, to thousands of the mass of the sun. And last but not least, it should be stable, or at least long-lived enough, such that it should live much longer than the age of the universe, because it is a fundamental ingredient of the evolution of the universe. So it has to be at least long-lived, but usually we consider that it should be stable. And then here you see on the plot on the left many different models of dark matter, and as a function, and what kind of masses and interaction, self-interaction it has, depending on the model. And all of these models are viable models of dark matter. Again, it's impossible to search for all of dark matter at once. So what we are going to do is that we're going to follow what's called the hunter's guide in order to search for dark matter in such a way that it's amenable to three kinds of the experiments. First, assuming that dark matter is here in the sky, the world is passing through dark matter, through this aura of dark matter that exists everywhere. First, we can set up a big target. And even though dark matter doesn't directly interact very often, if you set up a large enough target, maybe every once in a while we can see it. And these are the so-called direct detection experiments, where the dark matter interacts with the nuclei, you detect a recoil, and you see the signal. Or dark matter may not interact with itself too much, but it may interact every once in a while. So every once in a while, you can have dark matter annihilating with itself, and then you would see standard model particles, which should then, this effect should change the expected particle distribution of some standard model particles in the cosmos, like positrons or protons or so on and so forth. So again, direct detection, dark matter interacts with standard model. Indirect detection, dark matter annihilates with itself and gives standard model particles. And then there is this third axis here where we can try to produce dark matter at the lab. And this is completely complementary, because here we do not depend on the actual distribution of dark matter in the world, in the universe. We are trying to make it artificially. So the idea here is that you collide standard model particles and you try to produce it and see its effects. But then you're going to ask me, but Thiago, how can you see its effects? And this is what this talks about. And produce it in the lab really means produce it at high energy collisions. First, let me quickly go to the status of direct detection dark matter, okay? And even these plots may be a little bit old, but still just to give you an idea. So direct detection experiments like Xenon and Lux, they set these curves here, which exclude the presence of dark matter with a given mass and with a given cross-section of interaction in between the dark matter and the nucleon. Here you see the word wind, because usually these dark matter direct detection experiments, they focus on one particular class of dark matter, which is the weakly interacting massive particle. So the idea is that dark matter would be a particle with a high mass. High here means from a couple of tens to almost 1,000 GeV. And this very, very, very faint, so essentially compatible with weak interaction, cross sections of interaction between dark matter and nucleons. And you see here that you have different models and different, you have different experiments focusing on different areas of the parameter space. So you have here Xenon and Lux for heavy dark matter, and a lot of experiments, but including dark side for lower masses of dark matter under a couple GeV. Up to now, the answer is that no effect of dark matter has been seen. But there was a recent result, some excess of electronic recoils. So this is interesting, and we should keep an eye on this. I'm not going to talk about indirect detection because I really don't have the time. But again, the main experiment is essentially AMS2, which is a spectroscopy experiment that has been put in orbit, and it measures standard model particles, that so protons and positrons, and tries to compare the rate of particles it sees with what's expected from models of particle distributions in the universe. Now, I would like you to look at this slide for a while, and this is the regular slide that everybody speaks from Team Tate. Sure, we have different kinds of experiments, but as I have said, there are many different models of dark matter, and it's a zoo, okay, people. There are, I won't say there are as many models as there are physicists, but the ratio is not that different from one. The idea is that we should try to organize these models in a way such that we can focus the searches on different subclasses of models. So for instance, when the direct detection experiments, they were looking at winds, they were essentially looking at complete models. So the so-called ultraviolet complete models that are essentially full-fledged models that have all the parameters more or less understood and set, stuff like little Higgs, many flavors of supersymmetry, universal extra dimensions. But you don't need to go that far away into model building. Sometimes you can leave many parameters of your model unspecified, such that the simulations and the predictions you do can still be essentially correct for a super class of models. So for instance, if you leave some of our parameters unspecified, you can speak about so-called simplified models, where for instance, you just say, oh, actually the only thing that you need in your model is some particle that mediates the production of dark matter, like a Z prime or the Higgs quark or the Higgs boson itself, and the dark matter particle itself. But you don't need to build all your whole supersymmetric list of particles. You just need the basic things that you're searching for. Of course, then these things are not full-fledged models. They're not ultraviolet complete, but they can still make useful productions. If you want to specify almost everything, you go to this realm of effective field theories, where essentially you parameterize everything by just one single parameter in the denominator of a Lagrangian term. And this is what was done almost a decade ago, like contact interactions and dipole interactions. But this was not that correct in the sense that the approximations that you need to do to write an effective field theory were shown to be not quite correct for energies of the LHC. So right now, we, at least in the LHC, we are very focused in the simplified model scenarios. So what's my plan? My plan is to search for dark matter production at the LHC, either on the full-fledged models or on the simplified models. How do I do that? So I have to model this somehow. The main goal is to search for the direct production of a pair of dark matter particles, which I'm going to generally call chi, so chi bar. At LHC energies really need to write this as being produced by an explicit mediator, which you can say that has a spin, like a Z prime or a phi. And then you parameterize some couplings to the dark matter and to the quarks. And you have some Feynman diagrams here to exemplify. Assume you produce this dark matter by this proton collision and its subsequent production. How do you actually see the dark matter's production? And this is the problem. Dark matter doesn't interact. Dark matter will then leave no signal in your detector. So how do you actually see it? The answer is that you should find a transverse momentum imbalance. Remember, we more or less control the initial state of our collisions. So if you apply momentum conservation, then you should see that something is missing in the end. And the key thing is that these particles, they are invisible, but if they are produced by themselves, they are produced back to back. And then actually one balances the other and you don't see anything missing. So the key thing is that to search for dark matter in the LHC, you have to search for it recoiling against something else. So you have these diagrams where the chi bar pair is recoiling against something else. And this is the main search for dark matter in LHC. You have a pair of dark matter particles recoiling against something else. And then it's just a question of what is this something else. Of course, this is just a super simplified view of the thing. Of course, if you have a full model where you have a supersymmetry, a lot of particles being produced, then you have something else, or you have some particles which may be long-lived, and then the story is completely different. But from a bird's eye view, this is what to search for. You may ask me, Thiago, but why a pair of dark matter particles? And the answer is that one of the key things to make it stable in the models is that you add another quantum number to this particle dark matter and say that this new quantum number is conserved and dark matter is the lightest one that has this quantum number. So it has to be produced in pairs because this thing is conserved, but then the dark matter by itself cannot decay and conserve the quantum number because it's the lightest one that has this quantum number. So it's stable. So this is just a technicality. We in the LHC don't do all this modeling by ourselves in the experiments. So what has been set is the so-called LHC Committee Dark Matter Working Group. That is a set of theoretical physicists, phenomenologists, input from the experiments as well, that gives us guidelines and recommendations for some benchmark models on how to compare LHC results with results from direct and indirect detection. Usually, what they tell us to do is to do the search in the so-called simplified models, where you have essentially mediators which are either vector axial vector or scalar pseudoscalar and exchanged in the S channel, and assuming that the dark matter is usually a Dirac Fermi. But then these models are evolving such that we're doing searches on the T channel as well, or some more sophisticated spin zero mediators. So there is still, this is a work in progress, but to first approximation, in our searches, we follow the recommendations of the LHCC dark matter working group. Okay, I'm going to search for dark matter at the collider. I have to tell you a bit about the collider, or else you understand nothing. You have seen this slide about the LHC parameters many times. I'm not going to go through it. I just want to tell you that you produce new part, depending on the cross-section, of course, but you may be producing more than 1,000 particle signals in the detector at a rate of 40 megahertz, so it's a lot. And depending on this cross-section of what you're interested in one interesting collision in more than 10 trillion collisions at a time. So it's really an exercise of separating the wheat from the chaff. We cannot save all the collisions of the LHC. It's impossible. We don't have the bandwidth, we don't have the computer power, we don't have the disk, and we definitely don't have the graduate students to analyze it all. So we really have to save only what's interesting for us. The LHC, as you know, is a ring of 27 kilometers circumference in the French-Swiss border, and we have the 4 experiments here. CMS and Atlas are the general purpose instruments, and ALICE and LHCb are more focused on other aspects of proton collisions, like heavy ion collisions for ALICE and quark and heavy quark physics for the LHCb. One thing that I want to draw your attention to is one of the key strengths of searching for dark matter production at the LHC. And the fact is that the LHC can produce a real bunch of collisions. So unlike an experiment where you just set up a big target and you just wait for the dark matter to come and pass by, which of course depends on the density of dark matter in the universe. In the LHC, we can make many more collisions per second at a time. This is related to the luminosity of the accelerator. So I'm not going to go through the mathematics here, but when you see the slides offline, you can follow it. But the idea is that you take the bunch of protons, you make them really, really tiny and really, really concentrated, and then you make the crossing. And then since you have many protons on each bunch, you have many collisions happening per second. And this relates to the so-called luminosity of the accelerator. The problem is that if you run the numbers, and run the numbers is what's written here, you come to the conclusion that for the LHC, you actually, when you cross bunches of protons, you have many simultaneous collisions happening together. So something like 10 to 70 collisions happening at the same time. So yes, chances are that your interesting collision, the one that may be produced in dark matter, is here somewhere. But then you are completely screwed, because on top of your interesting collision, you have 10 to 70 collisions that are essentially junk, low energy collisions that just happen to happen on the same bunch crossing. So this is the price we pay to have so many collisions happening. Some of them happen at the same time, and again, you have to separate the wheat from the chaff. In the LHC, as I said, we have 2 general purpose detectors. I am part of the compact muon solenoid collaboration that runs a detector of the same name, Cms. We have the friendly competition from Atlas. And these are multi-layered experiments that you put around the collision point in order to determine the properties of all the particles that were produced in the collision. And these are state-of-the-art detectors that are equipped with charged particle trackers. So every charged particle, you can track it and measure its momentum. You can measure the energy of all the particles that are produced, because you have calorimeters, and then you have muon spectrometers, both in Atlas and in CMS, to measure even more accurately when muons are produced. So I'm not going to go through details here, but I invite you to look at the technical design reports, or even at the scientific outreach that these detectors put out. What's the key point? The key point is that Atlas and CMS are capable of reconstruction almost every known particle, because almost every known particle interacts with it. There are exceptions, which are, of course, neutrinos. Neutrinos don't interact only very weakly. They are not charged. They don't interact strongly. So usually they just cross the detector and leave no signal. But also dark matter has this exact same properties. So we are not able to see the dark matter in Atlas and CMS. So the key thing is that you focus on the transverse plane, and this is a technicality because you don't have the total momentum in the beam direction, so you can apply momentum conservation just in the transverse plane of the beam. And in this transverse plane, the total momentum is 0. So the key thing is that you reconstruct all the particles that you can. You calculate their vector sum, again, only on the transverse plane, and then you take the modulus, the absolute value of this vector, and you have the so-called missing PT. So if you look here, you see that if you reconstruct everything and something else is missing, this is indicative that something else escaped here, which may be, if dark matter was produced, maybe dark matter, but may, of course, be something else. So this was a crash course on dark matter. Now, how do I actually do the search for dark matter? This is a 3,000 strong collaboration running this, so I can barely start scratching the surface, but let me try to give you the ideas. The first obvious thing that you have to do is take the data. Remember, you cannot save all of them at the same, all of the events from the LHC. So we have to do a fast analysis online, choose which events we want to save, and usually we save 1% of 1% of all the events that are produced. And the key thing is to search the events that have exactly this missing momentum, missing transverse momentum signature. So here I have some plots from both Atlas and CMS of the efficiency of selecting these events online as function of the missing transverse momentum. And you see here that this is the so-called turn-on curve. So you can only actually select this event if the momentum that's missing is fairly high, something like 250 or 300 GeV. Only then you have close to 100% efficiency. So this is why when you read a paper on searching for dark matter, you see that they ask for missing transverse momentum of a couple of hundreds, because otherwise our efficiency of selecting these events is way too low. Here in slide number 18, please pay attention to the fact that reconstructing this missing transverse momentum may be problematic, because as I said, it's easy, right? Just reconstruct all the particles, sum all of them, and then take the absolute value. But nothing is easy, right? Because it may be, we may have problems. For instance, we may have a dead calorimeter cells, hot calorimeter cells, so essentially sensors that are stuck at 0 or stuck at 1, and then you have to disregard them somehow. You may have electronics noise. You may have non-collision source, so you have not only the beam colliding with the beam, but the beam halo colliding with the beam halo, and you have to take care of that. So you see here that if you don't do this cleaning, you see here on the plot, for instance, on the plot on the left, these are the data of no cleaning, and has nothing to do with the simulation. So you have to do all this cleaning to actually have these black points here that are actually more or less representative of what we expect to observe from standard model processes. Of course, at high values, at high missing PT, high missing transverse momentum, missing PT, then you have real source of a missing momentum. Notice here on the right that the resolution of our measurement becomes worse and worse with the number of primary vertices. This is related to the pileup, the number of collisions that happen at the same time. The fact that you have many collisions happening at the same time screws up the resolution of our measurement. So we have to pay the price for that. You can have more information here on our papers. The second thing is that even though in principle it's easy, right? Because you have missing momentum, you have dark matter, you have missing momentum, sure. But the opposite is not true, because there are real source of missing momentum in the standard model processes. So you have production of Z to neutrinos, W to leptons and neutrinos, and if you fail to reconstruct this lepton, then this lepton also appears as missing transverse momentum. Production of two bosons, production of PT bar. Sometimes you mismeasure, remember the resolution, sometimes you mismeasure the missing PT, so you think you have missing PT, but you don't. And all of the instrumental backgrounds that I just discussed. So here on the right plot, this is a plot from CMS from an analysis of only the 2016 data. And you have here the points that are the observed data. And all the colored histograms are standard model contributions to the spectrum of the missing PT. So in green you have Z to neutrinos, in yellow W to lepton neutrino, in blue dibosons, in red contributions from top quark, and in white and gray contributions that don't have real missing PT. When you take into account all of these standard model backgrounds, you see that you're actually seeing only the missing PT that you expected to see from standard model. And then you see here, it's hard to see, I'm sorry, but you see here that there is a dashed histogram. This is the fact of if dark matter were to exist, it would have this kind of effect. So it's really just a little bit on top of everything else that you see. Simulating these backgrounds is extremely hard because you have to simulate the hard interaction, the parton showering, the hadronization, the detector simulation. So doing all the simulation to see what's the effect of the standard model background takes a lot of time and has to be extremely validated. We're talking about simulating billions and billions of events, and every event takes something like 1 minute to do the full simulation. But Thiago, then it's pointless, right? I mean, if you look at this plot in slide 19, you have tens, hundreds of thousands of events of a standard model and just a few events of positive dark matter. What gives? The answer, of course, is that you have to search for some kind of variable that allows you to distinguish in between standard model background and dark matter signal. For instance, if you were to search for Z2 leptons instead of dark matter, it's easy, right, to search for the two leptons and you ask them to be on the mesh of the Z, like this. If you're doing some sort of search for SUSY, it's harder, then you have to devise super complicated variables. The key thing is to do the same thing for dark matter. You have to search for the right variables that, even though both events have missing transverse momentum, you somehow are able to distinguish in between events that have missing PT from dark matter and missing PT from standard model. Just a quick caveat here that sometimes, and this is becoming more and more common these years, you don't need to divide these variables by hand. You can let the computer do it for you, and in what's called machine learning. So machine learning techniques can allow you to automatically create variables that help to distinguish signal and background in all kinds of cases, but particularly for dark matter. I'm not going to talk more about this, but keep this in your mind, these words, machine learning, because this is one of the strongest tools in the experimental high-energy physicists these days. If you don't do machine learning, if you devise some kind of search yourself, the idea is that you have to search for many variables that allow you to separate signal from dark matter from background from standard model. I just want to draw attention to two things here. First, you want to design your selection to be as unbiased as possible. And you have to be careful to make a blind study because you want to avoid so-called observer bias and confirmation bias. What is that? You want to make sure that you don't look at the data and say, oh, but this looks like it could be dark matter. So if I just tune the cut like that, you cannot do that. So in order to avoid this happening, we design the whole analysis without looking at the data, just looking at simulations. How does this work in practice? For instance, if you're looking for a so-called monojet search, where you have missing PT recoiling against a high energy jet and nothing else in the event, you want to say, okay, I want missing PT above such and such 100 GVs. I want to have a jet with such and such energy and such location in the detector, and I want them to be more or less back to back, and I want the jet to be reconstructed, so on and so forth. But you want to be absolutely sure that you do all of this before looking at the data in order to not unbias yourself. Let me make a parenthesis here, okay? This is very close to what everybody has followed the COVID-19 situation last year. And you know that when you do this thing for a vaccine, you have to separate the people that take this test for a vaccine. They have to separate in between the people who take the vaccine candidate and the people who take the placebo. Both the people receiving either vaccine or placebo, they don't know which group they are, and the people who are running the test, the experimentalists, also don't know who are running the test, which people are in which group. We don't have the first problem, of course, because the protons aren't conscious, so the protons don't care. But it's exactly the same thing. We don't know anything before looking at the data. And then the idea is that you do the simulation of your standard model signals, your standard model backgrounds of your dark matter signals, and you compare one of the other. But remember that I told you that everything is complicated on the simulation. Then you may ask yourself, Thiago, how do you trust your simulation? And the answer is that I don't. So here, the possibility is, oh, I may fully trust the simulation, but it's not recommended, except if it's a background that's so small that no one even cares. So, 1 second. Okay, so what we usually do is that sometimes we do this data corrected simulation where you devise so-called control regions in which you expect that the background to your search is more or less equivalent to the one that you're searching for, but with subtle differences. For instance, Z2 neutrinos is very close to Z2 leptons. So you validate your simulation in the Z2 lepton samples, and then you transfer that knowledge, and these are the transfer factors that I say here, to try to estimate the Z2 neutrinos in your actual search. You have to do this for all of your control regions. So Z2 leptons, W2 leptons, TT bar, you have to make sure that everything that you have in your standard model prediction is similar, is validated in some kind of control region. And then you use this to estimate all of your irreducible backgrounds. So you see here some example control regions from the Cms Monojet Search. You see here W2 muons, W2 electrons, and neutrino, of course, Z2 muons, Z2 electrons, and top. You see here all the control regions from Atlas, and you see here that Here you don't expect dark matter. So here you just look at the data points, you look at the histograms and you say, that are the simulations, say, okay, I trust my simulation. Look, it agrees very well. So now that I trust the simulation, I can go and check it on the real search. What does checking the real search mean? I'm not going to give you a course in statistics, of course, but it's a deceptively simple question. Is the data that I'm observing, are the data that I'm observing sufficiently different from my predicted background such that I can exclude the null hypothesis? That means such that this cannot be the standard model. So this is cast as a hypothesis test where you have the null hypothesis that is the standard model and the alternative hypothesis, which is dark matter exists with such and such parameters. Of course, there is this whole point of the parameter of interest in which you have the dark matter cross-section. And then you have all of the other nuisance parameters that come into your hypothesis test, which is usually cast as a likelihood ratio. There is the luminosity, the particle density function, so on and so forth. There is also the fact that you may want to do a frequentist analysis or Bayesian analysis, but I'm not going to touch that with a 10-foot pole. What we usually do in the LHC is that we cast our hypothesis test as a let me try to not do to say this wrong, as a parameterized test of the likelihood of the profile likelihood ratio, where you write like this, and you then invert the hypothesis test to write confidence level limits for the parameters of interest. So in your case, you're going to write, oh, the cross-section for the dark matter production, where dark matter has this mass and these couplings, has 95% confidence level to be in this range here. That's what we do. Then you calculate the excluded regions. So you see here some examples from CMS, and everything in this red line here is excluded. So all these combinations here of mass of the mediator and mass of the dark matter, and then you go and compare to the other experiments. The ways to do this, there are subtleties that I'm not going to go through here. I invite you to look at these physics of the dark universe publications here, especially by people from the IIP, but that's the gist of the thing. So in a nutshell, calculate the limits on mass of the dark matter, mass of the mediator, and interaction of the dark matter with nucleon cross sections, and try to exclude as many of these as you can. In the last part of this talk, let me just give some of the latest dark matter results from both experiments, okay? Let's start with the Cms Monojet Search, okay? So in this kind of search, you have the dark matter pair recoiling against a quark or a gluon, and the idea here is that select large missing transverse energy. Remember, you want it large because of the efficiency that I have just shown previously. And you have some extra requirements such that you don't want the jet and the missing ET to be very close together, because this may mean that it's not real missing PT, it's just a mismeasurement, and you want the missing PT to be calculated in two different ways, and the two results have to be more or less among themselves, talk to each other. You have some control regions where you have one or two leptons or single photons, and you compare and see that there is good agreement here. And then in your signal region, you ask for the high energy jet and nothing else. So no leptons, no photons, no extra big jets. And then you look here on the left for data from 2017, on the right for data for 2018, and you see that the observed data agree with the standard model prediction. So this means no evidence for dark matter. So given this, you do the statistical analysis that I just told you, and you ask yourself, what are the limits on the dark matter that you can put? And then here are the results. For the axial vector mediators, the mass of the mediator has to be above 2 TeV, even for very small mass of dark matter. So here, everything in this black region is excluded. And for pseudoscalar mediators, again, you have these limits which are weaker, but still around a few hundred of GeV, 470 GeV. This is all done in the context of the simplified models, but then you can go to the full-fledged models, stuff like Higgs portal, fermion portal, ADD large extra dimensions. And here in CMS, we're doing even single lepton quark production to 2 neutrinos and 1 quark. And then you interpret the results in terms of the models of this, in terms of the parameters of these models. So the branching ratio of Higgs to invisible in the case of the Higgs portal model, or the number of extra dimensions in the case of the ADD model. And of course, there is equivalent Atlas result here that you can just check. But then the dark matter may, instead of recoiling against a jet, it may recoil against a photon. So again, you have a search, the so-called monophoton search. So Atlas again search for, let me talk about the Atlas search. That's, they search for missing PT above 200 GeV. They make many different ranges. So the missing PT has to be in such and such and such range. They have some requirements on the jets, which are very similar to the ones that we have. We want to make sure that the jet, if there is an extra jet in the event, is not giving rise to fake dark matter. They have control regions as well. And again, they exclude methods up to a few hundred GeV for axial vector or vector mediators. And depending on which mass of the this is the mass of the dark matter up to 360 and 520 for axial vector or vector mediators. But then if you focus on the mediator mass, it goes above 1 TeV. And then you have the equivalent CMS result here. But then, of course, you have all of the possibilities. So, of course, if you can recoil against a photon, you can also recoil against a Z. So now you have a mono Z search from CMS. And here we have some, besides the simplified model, some additional dark matter models, like 2 Higgs doublet model and Higgs portal models again. And here is the same thing. You select 1 Z boson with some PT. Again, more missing PT. Jets, some kinematics such that to make sure that your objects are well reconstructed. And again, we exclude mediator methods above a couple hundred GeVs. And these results are less restrictive than those from the published monojet results. But that's the key thing. You have to combine all of them to have the Uber result. And then you have the equivalent from Atlas as well. And you can go on and on. So Atlas has a monotop search. So now it's the dark matter pair recoiling against a single top quark. But why the top? Why is top special? Because third generation may be special. There is a lot of new physics studies about it. So again, here they focus on the 2 Higgs doublet model plus an added pseudoscalar mediator. And this is actually a full-fledged model. This is not simplified. They focus on the production of the monotop, both in the T-channel top plus jet and with the double associated production. And then the production is, the selection is search for one top, which means essentially 1 or 2 leptons, jets and B-jets, missing PT, because you want to have, again, the dark matter. You have some additional variables like the mass of the 2 leptons, or the transverse mass of the lepton, some control regions. Remember that you may have also TT bar contributions here. And they usually write these models, they usually write the results as a function of the mass of the additional pseudoscalar and as a function of an additional charged Higgs that is present in the model. And this is actually a supersymmetric model. So, sorry, it's not a supersymmetric model, but it also has an angle in between the two valves of the two Higgses that are in the model. This is a 2 Higgs doublet model. So they also put limits on the tan beta. And last but not least, CMS and Atlas both have mono Higgs search. So again, you have dark matter pair recoiling against a Higgs boson, but then you have all of the Higgs boson decaying here in whatever way they see fit. So BB bar, WW, ZZ, gamma, gamma. So this 2020 paper combines all of the Higgs channels, and that the target models are both the Z prime from the doublet Higgs doublet 2 Higgs doublet model and also baryonic Z prime model. I'm not going to go through the selections. It's more of the same. You want both a WW in 2 leptons or a ZZ into 4 leptons. And again, you see here that you exclude the Z prime less than 3 TeV for some factors of the additional pseudoscalar for a given tan beta, or you can exclude a range of tan beta for a given mass of the Z prime. Which brings me to my conclusions. Searching for dark matter in the LHC is one of our greatest quests, because the LHC really does have something to add with respect to the direct detection and the indirect detection experiments. There is a lot of complementarity there. We follow strongly the LHC dark matter working group recommendations. They give us the benchmark models. They help us do the combination and the comparison with the LHC results with the other experiments, and some comparison with visible mediator search. I'm not even going to touch that. We are finishing the analysis of all the run-through data, so the data taken from 2015 to 2018. You have to consider many different channels, so mono jet, mono photon, mono Z, mono top, mono Higgs. All the techniques are being continually refined. We do all the reinterpretations of one result into another model. We are trying to bring as many ideas into the foreground as possible, and we regularly present a smorgasbord of results in the big conference every summer. The LHC run-3 will bring additional 150 inverse femto barn that will sum to the more or less 150 that we already have, bringing the grand total to 300. And this will mark the end of the LHC era. But however, the high luminosity LHC is in the horizon, which will bring 10 times the luminosity, but at the cost of even more pileup. So we're just at the beginning. Exciting times are ahead. And with this, I want to finish my talk. Thank you all for your attention, and take your questions.
Thanks a lot, Thiago, for the very nice talk. So I think now we can take questions. Please, if you have questions, you can use the chat or raise your hand. And okay, maybe I will start with Dimitri. Please go on. I'll go next to you.
Thank you very much. Thank you very much, Thiago. It was a very nice panoramic review of the search of dark matter. So my first question is about this missing PT events. So how many of those do you regularly have at the LHC? It's a very basic question.
Yeah, but it's at least millions, right? Let me quickly show you here in slide number, I don't even remember anymore, but just for you to see, and not only for me to talk about it. Here we go. See here, there are, here we go, right? So here you have 10,000 events in the first bin. So the whole histogram has something like 100,000 events. But remember that this is after all the cleaning and all of the selection, and everything, so on and so forth. The number of events that we actually take from the mouth of the detector itself ranks on the millions of events per year.
So, for example, after you subtract the background, are there like any interesting events left, or do you how's this number compatible with the estimation of the standard model background?
So let me correct you quickly for a bit. Let's not talk about subtract the background. Let's talk about seeing if the number of events that you observe is compatible with the background, okay? Now, that said, the answer is no, right? We don't see excesses. That's what you're asking, if we see excesses. And the answer is barely, right? If you look here, you see in this ratio plots here, this is data. On top, you have data over prediction. And you see here that we don't have, we have sometimes 20% excesses here at the, maybe I can even zoom in. Yes. See here, you have a very slight excesses of 20% here at the tails, but you have amazingly good agreement. So if I were to say in terms of subtracting, I would say that no, the number of events after subtracting is compatible with 0. So no evidence of a BSM, no evidence of dark matter.
I see. So somewhat related question, and is also related to machine learning that you mentioned. So what can you do with machine learning now? Like one obvious thing would be to maybe help it to select interesting events in an experiment.
So yeah, I went very fast, and I apologize to everybody. The talk is far too long to fit in the allotted time. I have now seen that, but okay, next year it will be better. So what can you do with machine learning? So either you classify, right? So you train some kind of neural network to say, okay, this is background, this is signal, which is fine. You can also do some open-ended, unsupervised machine learning training that you just train real people in the industry do this. They train machine learning to detect anomalies like
like missing PT, for example.
Industrial. No, but yes, you train it to look at missing PT, but you can train it to look at general anomalies, something that looks different from normal. And because again, the example I was giving in industry. In industry, I mean, you can, if your industrial system is somewhat out of its parameters, something may blow up, and that's usually very bad. Here, you may here nothing is going to blow up, hopefully, but you may look at your stream of events and say, okay, these events look funny, and look funny is something that you can train for in an unsupervised way, such that it can, with less efficiency, of course, but it can look at something that is completely unspecified. So it helps remove bias, and it helps making sure that we don't leave anything behind. Just because we didn't think to look at it, we don't look. The second thing that machine learning can be used for is regression. So the idea is that reconstructing the missing PT is hard. So you may want to, you may want to calibrate, so on and so forth. But you may also train a neural network and let it loose in an event, and it will tell you, okay, for this event with these characteristics, even those that you don't know, that you don't really know about, that you didn't do the correlations, the true value of the missing T is there, is this. So you can also use machine learning in this different way to get the best estimation of a key variable like missing PT.
So once again about missing PT, is it believed that you basically define all the missing PT or sufficiently enough missing PT events, or there's still room for like additional events that you do not see that can, for example, change the results, the conclusions?
I think I failed to understand what you mean, Dimitri. Sorry.
Oh, I mean that you explained in the beginning, so that the experiment is quite complicated in the sense that there are many things going on, and you have to select important things, separate important things from unimportant things. And one thing you need to do is to register these missing PT events, and which you may register correctly. You may get all of them, or you might miss some of them. So that is it believed that you get basically all of them? Because when you compare to the background, of course, you have to compare with the experimental value, which you assume is the correct one.
So but the answer is that that's why we have these very high cuts in SMPT. So this reaction here in slide 17, this is actually measurement. We measure the efficiency of our selection with events from an unbiased source. So we just take the events randomly, and then we do this analysis and see, okay, so since it's unbiased, we can do it. Okay, so we see here that if we put the cut on the missing PT high enough, we have essentially 100% efficiency. That's the 100% approach in here. Of course, not 100%, but then you have a systematic uncertainty, and you take care of that in the analysis. But that's why we put the cut so high. So with these high cuts on missing PT, we are 99% confident that we're getting essentially all of the events. Of course, we would like to have lower cuts, right? Because then we get even more events that can come from dark matter. But then it starts being more complicated. And that's where, for instance, better measurements of missing PT, for instance, for machine learning may help us. But with these numbers that we have, 250, for instance, you see that we are essentially at 100% efficient.
Okay, great. Thank you. Thiago, I think you are muted.
No, I'm not muted.
No, I am.
The other
I was muted. So, sorry, Fabio, just because the graph is on the screen. So it's is it possible in the future to increase this efficient, or something that it's not this PT to go to lower PT, or?
So yeah, it is possible. Of course, it's a bunch of hard work. So one of let me show you the wizard behind the curtains, okay? What's the problem? The problem is the problem is the level 1 trigger. So in the level 1 trigger, right until now, we have a hardware trigger that just reads the calorimeter information, and that's somehow low resolution. One thing that is on the works for the future is, and for the future means high luminosity, let's see, is to have information from the tracker and which is much higher resolution at the trigger level, and to do some kind of sophisticated measurement of the missing PT even at the trigger level, even with particle flow. So yes, the good news is yes, that it's possible, it's on the works. Please read my technical design report that we have just put to show how we are going to do that. It is going to get better, except that it isn't, because the high luminosity LHC actually has 200 pileup. So remember this plot here. Where is it? See this plot here where the resolution gets worse with more parameter vertices, so higher pileup. So what happens is that the two effects will cancel. So I can promise it's not going to get worse, even though we're going to have 10 times more data and 4 times more pileup.
Thank you. So please, Fabio, go on.
Okay, Thiago, thank you for the word. Thiago Tomei, exciting seminar about dark matter, right? Very happy to see you speaking. Could you come back to the beginning of your slides? In the beginning, you showed the graph with the dark matter particle candidates with axion, axino, and other particles. This one, right. As far as I understood, this graph is a theoretical statement, right?
Yes, this graph is a fully theoretical statement.
Right.
These are just the masses and the interaction cross-sections of all of these models.
So this estimation of the axion mass was made in what, with what model?
I have no idea whatsoever. This is just to illustrate that there are many different models that have dark matter candidates. I have literally no idea.
Right. Look, in the sequence, I would like to understand the difference, because as far as I understood, in the major part of your experimental results, you were talking about the fermionic nature of the dark matter, right?
Right.
As you showed, there is a increasing investigation, many questions to answer. Nowadays, the main current of investigation is about the fermionic nature, or that there is some increasing belief in the bosonic nature?
In the LHC, you mean?
Yeah.
So in the LHC, we are not sensitive to that, because again, we don't detect the dark matter. So we are forced to, the only things that we make statements about in this sense is with respect to the spin of the mediator. So it's either a pseudoscalar or a scalar or whatever. But the dark matter itself, we have a very, very small handle on each characteristics of its fine-tuned characteristics, let's say. Of course, the mass of the dark matter enters directly on the kinematics, and to that we are sensitive. But the spin, we are essentially blind to it.
Right. Thank you for your answer.
Maybe a quick follow-up. So are there any excluded regions in this plot, or everything which is shown here is allowed? I think you mentioned that all of these are viable.
There are definitely, no. There are definitely excluded regions here. But notice the scale, right? It goes from 10 to the minus 30 to 10 to the 18, and 10 to the minus 36 to 10 to the 24 picobarns. So the excluded regions are probably super tiny here, but it's the exact same excluded regions that are shown here in slide 39. But the scales are, of course, completely different.
Okay.
Again, because here in the LHC, we focus essentially on simplified models and some models which have characteristics which are amenable to an LHC search. Of course, if dark matter turns out to be something that is completely impossible to see at the LHC, good luck. Let Xenon find it. But so that's the key point of the complementarity.
You mentioned, you talked about the excluded regions from the LHC, right? But there are also other experiments that probably put some bounds.
Sure, which is what I showed here, or sorry, again, I probably went too fast, but what I tried to show here in slide 27. So you see here, for instance, for one kind of dark matter scenario. So this is the spin-dependent dark matter. So this is probably for axial vector mediator. So you see, you have here some exclusions from the LHC. So you have here, let me zoom in. You have here boosted jet, dark matter plus whatever. And then you have exclusions from the direct detection experiments. So you have here Picasso, Pico, Super K, and Ice Cube into channels. This is what we do mostly under the guidance of the LHC Dark Matter Working Group.
I see.
Okay, so
There was maybe a question from Yasara.
yeah, but
She still has a question.
Okay, thank you so much. Excellent talk. Okay, some questions were made for the professors, but I have two questions. Using computational tools in high energy physics to obtain the channels proposed in page 8, where the gauge boson are scalar decays in the D possible particles of the dark matter. But how do you know the exact difference that our possible dark matter candidates are not neutrinos? Because the target is null in some cases and invisible. So how could you improve those results for a more accurate analysis in two cases? Other question is, what is the base? The best way to find the dark matter searches to the D electron channel instead of D1 channel, because you know with the last results the possibilities of the universality violation with additional interactions. Or what you think the better way is choose the D lepton channel in the LHC.
Okay, let me first let me answer the second question. We don't we use the lepton, the neon, and the electron channels usually as control regions for our searches. So you're right, we assume lepton universality. And we cannot do otherwise, okay? Because the idea is that we're searching for one different thing from the standard model. We have one moving part, which is the dark matter, its mass and its spin, and the mass and the spin of the mediator, the mass of the dark matter and the mass and the spin of the mediator. If you have too many moving parts, it's over. You lose most of your predictive power. So we don't do that. We assume lepton universality and run with it. And at the level that we do it, it's enough, right? Because you see lepton universality violation in a very, 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 very constrained corner of the space of parameters in the RK star, blah, blah, all that thing that we know. But if you actually go in third and count these going to electrons and these going to muons, which is what's important for us, is the same. So my answer to the second question would be the levels of lepton universality violation that we observe at LHC are insignificant enough that for this, we don't care. And the first question I didn't understand. So if you could summarize.
Okay, thank you so much for your answer.
I think the first question was more about how do you know that the dark matter is not neutrino, for example.
Well, I think that is, I think there are cosmological, astronomical results that say that it has to be cold dark matter. So it cannot be neutrinos as far as I understand. Well, it cannot be in its entirety neutrinos. But again, this is the whole point. It's a separation of concerns. Dark matter, as I said in the beginning, dark matter is, from my point of view, a bunch of gravitational weirdness on the sky. Assuming that it's actually a particle, then I'm going to search for this particle in the LHC. But then people have to convince the collaborations, convince the community that this and this and this model are worthy to look at. So simplified models are good because they are easy to deal with, and they're easy to simulate, and the results are more or less okay for many different more complicated models. Some things are fan favorites, like ADD or supersymmetry, and then we always search for them as well. Higgs is important because Higgs is invisible, so maybe there is something that only the Higgs couples to, and that thing is the dark matter, so we search for it. But why? Because it's the Higgs, right? The Higgs is, important. But I don't know what dark matter is. If it comes out a good model that, it's actually neutrinos that couple with whatever in such way, sure, we can search for it, or we can do reinterpretation. So in that sense, I am agnostic.
I think you are kind of corroborating this neutrino hypothesis, because this is what you see. I mean, you don't see anything but neutrinos in the missing PT, for example. Right?
I would say that I don't see the neutrinos. Yes, but I get your point. Yes.
Okay. So I have just about the simulations of the background. What is the state of art of it? How good it's about the background, the simulations? Yeah.
So the state of the art is what I'm showing here. Okay, so usually what we have right now, we simulate the hard interaction. That you factorize the hard interaction and the rest of the proton interaction. The hard interaction, usually these days we manage to do everything at NLO with MedGrav 5 and POHAG. We have some K factors to account with the higher orders. Parton showering hadronization is still the two workhorse, PTA8, HARID 7. Detector simulation is still always done with GEANT. So it's the only game in town. And if you ask me how good it is, that's why we have this, right? That's why we have this validation here. So you see that
Okay.
it's pretty good.
Okay. So there are any further questions? I'm not. Okay, so thank you, Thiago, a lot again for the seminar. Thanks everybody for participating, and see you all in the next seminar. And okay.
Thank you very much for the invitation, Thiago and Dimitri. I hope that next time I'll be able to be there in person.
Okay, thanks.
Thank you, Thiago. You're very welcome.
Thanks, cheers. Bye-bye.